just like that you see along the Henley. Right? So that's important to recognize, and I'll come back to that when we go further along. But that is countercurrent flow, vasa recta. Notice they're associated along the Henley. They have an ascending and an ascending or countercurrent flow. Very important that they aren't in the transverse fashion like this. Okay? Yes.
So do they actually have two ascending portions like in the picture?
It
looks like it's
you
an
know,
ascending with two ascending splitting off.
yeah, it does look like that, but artists have been pretty generous by putting those up there. Yeah, no. Generally, I mean, also you can have several next to each other, and you couldn't appreciate which one is associated with which. But you know, at least in our mind's eye, we can picture one following the descending, one following the ascending. It doesn't have to be two, but good point there. Okay, so we have an orientation now, right, of our blood vessels. Afferent. We have our capillary, right? Glomeruli. Isn't that strange? That's a strange orientation, isn't it? Arterial, capillary, another arterial, and now more capillaries. Very strange. That's very, very strange. So only place you find that arrangement right there. Kidney. Okay. So, kind of quick summary of what I just mentioned here. We don't care again about all these segmental branches. Like I said, we obviously answered these things already when we did that. But we come all the way down here. I've highlighted the most important area here of our blood vessel discussion. Afferent, capillary, efferent, peritubular, and the vasa recta. The feeder vessel, the drainer vessel, and providing then those two capillary networks. So far, so good. Again, this is not of interest, but I have to at least say, hey, it doesn't just go from the artery into the arterial. That would be bad news. So there is a pathway. So if you had to circle something, circle what has been indicated right there. That's what we really care about. Can I get past that? Okay. All right. So let's take a look at the capsule for a moment. All right, the capsule here. It has two layers. It has two layers. Does anyone recognize this picture? Yeah. This is what? We're looking at the kidney, aren't we? Yeah, looking at the kidney. And so you may even, I know you had the answer here. We're looking at the kidney, of course, and this is a slide that we used. And this is the area that we were looking for, simple cuboidal everywhere, right? Remember that? If you're not, that's okay, but maybe you recognize that. So what are our layers of the capsule, okay? We have a parietal layer and a visceral layer. We do not care, okay, about the parietal layer, but I'm going to point it out because I would be, I would feel bad if you didn't know what that was, okay? This is the parietal layer, okay? This is the parietal layer that I'm touching, right? Lines the wall of any structure, right? Okay? This whole thing, of course, is our renal corpuscle, as you probably realize. But this is the parietal layer. It really is simple squamous, not a big deal, and that's about all I'll say about that. Okay? Not the big ticket item for our layer. But the other layer, which is going to be called what? The visceral layer. This is the visceral layer. I'm touching it. It's not that big ball, okay? It's what I'm touching right here. I can't come up here and say, it's right there, okay? This layer that's on here is the visceral layer of Bowman's capsule. That's the layer we care about, all right? That's the layer we care about. So we have the parietal layer, again, I said I was going to say it again, parietal layer, and then the visceral layer right here. So now, what is this space called? See that space? Any guesses? You could name it because you already had an eponym or two. What is it? It is Bowman's space. Name the fluid in there. Bowman's fluid, yes, or ultrafiltrate or filtrate. Very good, okay? So we've got the visceral layer, Bowman's capsule, right on there, okay? And then we also have Bowman's space with Bowman's fluid, right? What could be in Bowman's fluid? Or I should say this, better than this one. Take a guess what should never be in Bowman's fluid, unless you have a pathology, which we're not talking about those. What should not be in Bowman's fluid? Blood, like what? Now, I'll give you the idea. You separate this one because we know blood is plasma, but also formed elements. So now your choice is what? Yes. No formed elements should be in there. No formed elements. No RBCs, no WBCs, platelets. So what then would be in here? Pretty much everything that's plasma. Plasma would be in there. Yeah, that's right, plasma. Okay? So would you think that Bowman's fluid and plasma would be pretty much identical? Indeed, it is. There's a few differences, small differences that we'll discuss, but generally it's pretty close to plasma in osmolarity. Pretty close. Okay. So, we've got our layers here, right? Now, we have an idea here that we have filtration going on, right? In this glomerulus filtration. We call that glomerular filtration. Does it sound like then that if we've got that afferent arteriole feeding blood into this structure, okay, under pretty good pressure, forces fluid across the capillary wall, although some things do not pass, like we just identified, and then some things end up in here, okay, which in the moment space, we have to figure out what is composing now of this filtration membrane, okay, because it's not just going to be what? Visceral layer of Bowen's capsule, right? Okay, not just going to be that, has to be other things too. If it's capillaries, we're looking at simple squamous, right? Simple squamous, or which I have up here, endothelium, okay? Endothelium, right, of the capillaries. This is now forming our filtration membrane, because we're forcing something across the capillary walls, which we're going to call our filtration membrane, but there's certain layers to this we have to investigate and figure out why some things pass and why some things do not pass, okay? So we have capillaries, and being endothelium, or being epithelium if you want, it always has a what? A basement membrane, and that's the other layer now, okay? Now we have specialized cells that are unique in that they have little feet on them, okay? And so we've got a capillary like this, let's say it has capillary like that, and now we have specialized cells that wrap around the capillary like this, and little feet on them, okay? They're called podocytes. Podo refers to foot. Podocytes. Cells with feet on them, right? And now between their feet or foot processes, you find something known as a what? As a slit diaphragm, or just a diaphragm if you want, that's okay. A slit diaphragm, okay? Or sometimes even called filtration slit diaphragm, choose your word, right? Okay? These are between the feet of the podocytes. So now we've just designed our filtration membrane. Endothelium, basement membrane, okay? And now we have these podocytes, specialized cells with feet, and that wrap around the capillaries, and between their feet are filtration slits or slit diaphragms, and that again is our filtration membrane. So, why would something get across that membrane and into here, or why would something not be able to get across that filtration membrane into here? Give me some ideas here. Or, yes?
By the size and charge?
Yeah, she said by the size, things can pass, okay, if they're small enough. Things that are big like RBCs, WBCs, and platelets, they're not going to pass. So size is pretty straightforward, or at least obvious, I hope, because the fenestrated was little windows, right? They're not big garage doors where things can pass, but they're little windows, so small things can get through, big things cannot. So the filtration membrane selects for, or filters by size. But now wait a minute, okay? There are things in the plasma that are small enough to pass, but don't. These things are negatively charged. They are the most abundant plasma protein. They're in charge of creating and maintaining osmotic pressure, and they are known as albumins. Albumins have the capacity to pass through that tiny window, those tiny fenestra, but do not. They are negatively charged, so they are repelled. Okay? So maybe you're saying, then again, how does this filtration slit diaphragm and membrane work? It filters by size, and it filters by charge, because well, maybe you can tell me, why would the negatively charged structures like albumins, which could pass, and believe it or not, some actually do pass, they make a way, not every filtration barrier is perfect, but they will be recovered, a few of them will make its way through, so nothing is perfect. Some things do pass, but they will be recovered. And so, why would they be repelled? What's a major component, I should say, not the only structure here, major component in basement membrane that would provide for a negative charge that will repel these very small plasma proteins? Same thing that we learned in the blood chapter. It's in the basement membrane. It's not the only negative. Yeah, it's collagen. It's in collagen, okay? collagen is in the basement membrane. Collagen's negatively charged, repel those negatively charged albumins, even though they could fit, okay, they could pass, but they repel. So you have structures like collagen, okay, structures like collagen in the basement membrane. You also have molecules known as nephrins and podicins. These are also negatively charged that you find in those filtration slit diaphragms. Podicins and nephrins, okay, small molecules negatively charged that repel negatively charged ions, or molecules like albumin. Okay, nephrins and podicins, that would be part of the filtration slit diaphragm. Okay, that would be part of it. So you put your hand over like that, filtration slit diaphragm between nephrins and podicins. These negatively charged molecules that again serve to select for and filter for size and charge. That's how this glomerular filtration works, selecting by size and charge. You know size because of the openings in the fenestra, but now charge is due to the negativity. The collagen even was between the filtration slit diaphragms, podicin and nephrin. Okay, don't forget the size and charge. That's a test question guaranteed. How does the filtration membrane select for size and charge? Right? Or just size only, or just charge only, or just size and charge, or neither, you know. So make sure you remember size and charge. Okay. So let's take a look at what it looks like here. So an enlarged nice view here, afferent arteriole, we can now appreciate, and this has been sectioned here. This has been sectioned, you see inside, little RBCs inside of here. And now you can even see these little podocytes, I shouldn't say that little, but the podocytes here, and these little feet that have been nicely drawn, little feet like there, kind of interdigitating around the capillary there, and then we can even see the flow of fluid there as well. Okay, so that's afferent arteriole, and look at this. Isn't that something? What's happening there? It looks like there's a large input, right? Afferent arteriole has a larger lumen than the efferent arteriole, doesn't it? You think that's in this drawing? You think that's accurate? That is accurate, yes. There's a large input and a small output. What do you think then would go on in there? Input, big input, and a small output, so it sounds like that would be increase in pressure, absolutely. Increase in pressure there, which would promote filtration. Promotes filtration. That's one of the reasons why you do not see reabsorption occurring here, because of the high pressure relative to capillaries now. We're not talking blood pressure that would cause an aneurysm to burst, but relative to other capillaries, the pressure is higher because of the large input and small output, all right, or lumen size of afferent versus efferent. Okay, that's one reason why filtration only occurs here. Another reason is actually because the surface area is so great. Okay, there's a huge surface area, so that we have filtration going on throughout the entire length of the capillary, and the pressure is so high, it's only filtration, no reabsorption. So, as our fluid is pushed across there, we end up with our filtrate right here, and now what do we have? We're now into the proximal convoluted tubule at this point, and so what is the osmolarity approximately of this fluid right here? Not much has changed, not much has changed. You know, it's still about 300 milliosmoles right in here. Okay, when it gets into here, what is it? Just about the same, 300 milliosmoles. Okay, 300 milliosmoles. So not much has changed in the filtration process. Here, but things do have to change as it migrates from PCT to long loop Henle to DCT to collecting duct. Things do have to change, and they will change, because tell me some components that are in here. Besides the usual ions, okay, we've got that hammered out, at least what you might expect. What other things could be, though, in here that we do not want to have make its way through now the PCT and the long loop of Henle, the DCT, and the collecting duct into the urine eventually? What do we not want? So what other things could be in here? What's in the plasma? Like maybe amino acids? We want to save those, don't we? Okay. What about maybe glucose? You want to save that? That's in plasma? Yeah, that's in plasma. So as this is pushed across here, we really only pretty much kept out what? RBCs, we've kept out platelets, albumins to some degree, a few sneak by, don't have to be recovered, okay? And they do have to be recovered. But we pretty much have plasma over here, everything, all the good stuff in plasma, amino acids and glucose are pretty big ticket items there that we want to eventually recover, okay? Any ideas what process those would undergo? Because we've just done here glomerular what? Filtration. Now you say, hey, there's some good stuff in here and we want to save it, so let's have this tubular reabsorption. Tubular reabsorption, yes, tubular reabsorption. Okay? Tubular reabsorption. If we just kind of take a step back and say, well, if tubular reabsorption is occurring there, what kind of apical modifications might you expect on these cells? Remember, if you think about an epithelial cell, okay, we can draw a simple cuboidal cell, because the kidney is littered with simple cuboidal, and this is the basilar area here, the lateral area here, and this is the apical surface here. What type of apical modification might you expect to see on cells that are in the PCT that are actively reabsorbing stuff like glucose or actively reabsorbing stuff like amino acids? Anybody? Yes, microvilli. You'd expect to see, yes, a whole bunch of microvilli on those apical surfaces of those cells, or on the apical surface of those cells, okay? Extensive microvilli. Again, the microvilli increase the surface area for absorption, okay? In this case, though, we're going to call it reabsorption because we have things that left the blood, they're going to be taken back and put back into the blood. So, increase the surface area for reabsorption would be the better and proper term there. Instead of absorption, I need to screw that up. But reabsorption, that's what you expect to see, okay? In fact, most reabsorption, okay, and where's this? Let's see if we can figure this out. Most reabsorption occurs in the PCT. 65% of the reabsorption that occurs in the nephron goes on in the PCT. 65% or so. That's a value that I actually kind of would hold you to as far as most reabsorption occurs. You know, if you look in a book, it might say 65 to 70. I'm looking at most, so kind of be aware of that. That's not a number I would hold you to specifically, but most reabsorption goes on in the PCT, right? So we know there's apical modifications, which are the microvilli, okay? Which direction are things going here? If it's reabsorption, and we want to put it back into the blood, what would you expect to see if I drew some stuff around here? This is where you gotta kind of put a couple things together. We're right here in the PCT, okay? Right there in the PCT. Now stuff is in the PCT, like glucose or like amino acids. There's lots more things, but these are things they're really pretty useful, especially glucose. That's got a great word to it. Okay, PCT. We're in there, and they said, hey, we're going to reabsorb this stuff. Where's it going to go?
PCT into the capillaries?
Yes, it's going to go from the PCT into these capillaries, specifically here, peritubular capillaries. That's where it's going, back into the blood, reabsorbed back into the blood. Okay, so things like glucose, things like amino acids, lots of other things as well too that you'll see. But that's the direction of things that are being reabsorbed, is they're in the tubule, they have been filtered, okay? They have been filtered, and now they're in the PCT, and they need to be reabsorbed. And there's lots of processes how things will get reabsorbed, okay? Active, secondary, active, facilitated diffusion, all these kinds of good things that we'll look at. But it will be going back into now capillaries or blood, peritubular capillaries. Right? Clear that out? Or put it up? Not out, but up. Okay, so we've got the PCT hammered out there as well. Bear in mind that you've got this afferent, a large lumen for the afferent, and a small efferent. It's nice to say, yes, that is indeed, I appreciate that, but also recognize the reason why our blood pressure is higher in this capillary system, and that's one of them, because of the high input, lumen size, and low output. Okay, that's why filtration is going to occur in this group of capillaries. You don't see it anywhere else. Okay? All right. So, And there's another picture now of our podocyte with the basement membrane and our fenestrated type of endothelium there. Another picture of our visceral layer of Bowman's capsule. Again, we don't care about the prior. Okay with that? What if, for instance, okay, what if, for instance, that, you know, we said, you know, if we want to push stuff across here, right, we push stuff across here like this, we're going from here into there into the, you know, Bowman space, and, you know, sometimes, you know, we don't necessarily want to produce a whole lot of filtrate, because filtrate ultimately can lead into increase in urine output, okay? So, we already said, hey, there are ways to limit the amount of blood getting into the kidney, right, okay, which would reduce our urine output, raise our blood volume. What if there are ways to take our foot processes here, okay, and make them go from, say, this, okay, to this, close them down? What if we did that? Do you think that would help significantly, keeping the filtrate from being formed, keeping all urine from being formed in great volume? And we always have to produce urine, you know, that's, we can always do that, okay? But that, okay, that fact there is important because we can regulate the amount of surface area available for filtration. If we close down that surface area, we reduce the amount of filtration formed, filtrate formed if you want, reduce the amount of tubular fluid, reducing then raising again our blood volume, raising our blood pressure. Okay, so not only can we limit blood flow with the sympathetic, we also can close down these podocytes, these pedoceles, if you want, these foot processes, close them down and reduce the amount of surface area available for filtration. Okay, we can do that. There are cells that actually have the capacity to communicate with these podocytes that I haven't shown just yet, that are stuck within the capillaries themselves that serve to do just that purpose, close down that filtration membrane. Pull those podocytes, or those pedoceles, the fetus of pedicele, okay, close it down like that, so that now you have reduced surface area for filtration. Okay, does that make sense? So again, not only can we limit blood flow, but also close down our feet, okay, close down surface area, and we produce less filtrate, greater blood volume, greater blood pressure. Okay, so far so good? Okay. Another view of that. Another picture there, I don't know why I have so many pictures of this, I thought it was kind of neat, but you come across so many, I don't know which one to say, but you can certainly appreciate our lumen size there and there, okay, and the PCT, and the little podocytes wrapped around there too. Very nice. Alright, so we can answer these, right? What gets through the filtration membrane? All normal plasma component except for what? Formed elements? Yes, yes. Except for formed elements, yes. And of course, albumins. Oh, yeah. What two reasons? Why for two reasons? Size and charge. That's the answer to that, size and charge. Why is that glomerulus so good at filtration? Large input, small output, and surface area. Huge surface area. That's why it's so good at filtration. And that large input, small output translates, of course, into higher blood pressure, which is important. Or you can even call it glomerular hydrostatic pressure, couldn't we? Previous chapter, we could call it that if you wanted. So far, so good? Yeah. So we got glomerular filtration. What drives that filtration process? Pressure, yes, and you said it. Blood pressure, yes, that's what drives it, okay? You can call that blood hydrostatic pressure, or we can call it more specifically glomerular hydrostatic pressure, whichever one you want. But that's the driving force, okay? Do you think there are other opposing pressures there? Think there's maybe some type of osmotic pressure there in the capillaries? Absolutely, there has to be, okay? But they're not strong enough to override and take over the process. It's always going to be filtration there, right? Always filtration. There's going to be, of course, osmotic pressure there saying, hey, you know, I'm drawing fluid in, I'm not going to let fluid leave, so I'm not strong enough, though. It's going to be forced across, okay? That's why filtration will always occur there. Blood pressure or blood hydrostatic pressure or glomerular hydrostatic pressure, whichever name you want, is always higher. Okay? All right. So, now we can come to an area here where we have a little bit more of anatomy histology to hammer out, because when you look at structure, it governs function. Now to kind of look at this closely, there's our nephron, and it's been kind of sectioned here. We can kind of see where the distal convoluted tubule has making its way up in between our arterioles. Which one is which? Which one is the arrow here? That appears to be a little bit larger, so that's going to be what? The afferent arteriole. That's the efferent arteriole. Now my point here is the distal convoluted tubule makes its way up in between those two arterioles, afferent and efferent. Okay? And when it does that, modifications occur. One of which is in the wall, okay, the wall of our DCT. Right? Wall of our DCT. Okay? That's a modification that I'll get to in a moment. You also can see there appears to be some other purple cells scattered about in here. Okay? And there's even a layer of cells kind of reddened in this view, reddened cells here that are surrounding, they're even over here too, right there and there, okay, surrounding our afferent and efferent arterioles. All of which I pointed to, this whole kind of, purple cells and these red cells here, form the entire collective category of juxtaglomerular apparatus, or JGA, right? That includes that kind of unique passage of the DCT going up in between the afferent and efferent arteriole, and then in the wall of the DCT, you find a group of cells that look like a dense spot, hence the name macula densa, dense spot right there, okay? And then also of note, you can see some purple cells scattered about in here, there's even some in here, and even some red cells here, all right? Those all, again, fall in the JGA, and the cells that are here, okay, purple ones, are called mesangial cells. Meso refers toward the middle or midline. Not really midline, but middle if you want. Mesangial, in the middle of blood vessels. What blood vessels? Our capillaries. Mesangial cells, okay? Then we have these red cells here, here, and here, and here, called granular cells or granule, whichever word you want, granular or granular cells, okay? These are the three groups of cells that form the collective category of JGA, juxtaglomerular apparatus. Okay, so we've got mesangial cells right there. We've got our macula densa right there, a dense spot, and even you can see these on our models in lab. They're pretty clear on there. So that, and then the vessel and the cells that are associated with our blood vessels here, which are known as the granular or granule cell, whichever name, which is called the JGA. Okay. Any questions on the members of these? So far, so good? Okay, I don't know if we've got much more time left at all. I'm not going to start the function here. I'm not at all the good functions. We have to know the functions, of course. But I've covered maybe about 30% or so of the chapter. I think maybe 1 through 8 or 9 slides. We have 2 more days for this. It gets very convoluted as we go through this more and more. So please read the chapter, read the notes, because it gets very twisted, right, as we go through. So, any questions on this at all? Okay, we have a bit more histology to go through, but then we'll get into physiology.